Chapter 6, Module 1. In this module, we shall see how a group can be associated to a pointed topological space and how the continuous functions between pointed topological spaces induces homomorphism between the corresponding groups. We have already seen in the previous modules that we can construct a set consisting of loops based at some point x0 of the topological space X, and that set can be partitioned into disjoint equivalence classes by the relation path homotopy. Now, in this module we shall first see that we can define a composition on this collection of equivalence classes such that it forms a group. Suppose P be the collection of all loops in X based at some point x0 of the topological space capital X. Now, if x(x0) is a pointed topological space and pi 1 x(x0) stands for the collection of all equivalence classes of loops based at x0 arising from the equivalence relation that alpha is related to beta if and only if alpha is path homotopic to beta, then the pair class alpha class beta goes to class alpha composed beta, that is class of alpha star beta is a well defined binary operation on pi 1 x(x0). So, what we are doing is taking any two elements of pi 1 x(x0), one is class alpha, the other one is class beta. Composition of alpha, class alpha and class beta is now defined as the class alpha star beta. If class alpha is equal to class alpha 1 and class beta is equal to class beta 1, then since alpha is homotopic to alpha 1 and beta is homotopic to beta 1, we have alpha star beta is homotopic to alpha 1 star beta 1, and therefore, alpha class composed beta class is the same as alpha 1 class composed beta 1 class. So, that means the operation, the way we defined there is well defined. Now, for any pointed topological space x(x0), if we take the collection of all equivalence classes of loops based at x0, that means the collection pi 1 x(x0), then pi 1 x(x0) with this composition defined as alpha class composed beta class is equal to class alpha star beta forms a group. This follows from the following facts that we have already seen earlier, that alpha star beta star gamma is path homotopic to alpha star beta star gamma. So, the composition of equivalence classes is associative. Now, we also know that alpha star Cx0 is homotopic to alpha and Cx0 star alpha is homotopic to alpha. So, that means Cx0 class will serve as the identity element of the group pi 1 x(x0). Now, alpha star alpha inverse is path homotopic to Cx0 and alpha inverse star alpha is path homotopic to Cx0, which shows that alpha inverse class is actually the inverse of class alpha in the collection pi 1 x(x0). So, we get pi 1 x(x0) is a group under the operation of composition of equivalence classes. This particular group is called fundamental group or Poincare group of X based at x0. The definition of fundamental group depends on the base point x0. So, fundamental groups are associated to pointed topological spaces rather than topological spaces in general. However, if capital X is a topological space and x1 and x0 are points in capital X such that they are connected by a path, then the corresponding fundamental groups pi 1 x x0 and pi 1 x x1 become isomorphic. How do I prove it? Suppose we have a path omega connecting x0 with x1, then omega 0 is x0 and omega 1 is x1. Now we define f omega from pi 1 x x0 to pi 1 x x1 by f omega of class alpha is equal to omega inverse star alpha star omega that class. We show that f omega is well defined. So, we take two members from pi 1 x x0 which are equal, that means class alpha is equal to class beta, that means alpha is path homotopic to beta based at x0, and therefore, applying the theorem for products, we already have that omega inverse star alpha star omega is path homotopic to omega inverse star beta star omega. So, f omega of class alpha and f omega of class beta are equal. Now, alpha is homotopic to alpha 1, beta is homotopic to beta 1, that implies alpha star alpha 1 is homotopic to beta star beta 1. So, now f omega of alpha class composed beta class is equal to f omega of class alpha star beta, which is class of omega inverse star alpha star beta star omega, which is equal to class of omega inverse star alpha star Cx0 star beta star omega. Why we can do this? Because we know that alpha star Cx0 is path homotopic to alpha and everything is within the equivalence class. So, we can well replace alpha by alpha star Cx0. So, now again omega star omega inverse is path homotopic to Cx0 and therefore, Cx0 can be replaced by omega star omega inverse. Now, we apply the associativity, that means within the equivalence classes associativity works, and therefore, omega inverse star alpha star omega class composed omega inverse star beta star omega class is equal to the given one, and therefore, we have f omega of class alpha composed f omega of class beta is equal to the starting point, that is f omega of class of alpha composed class of beta. So, that means f omega is a homomorphism. Now, we intend to show that this is not only a homomorphism, it is an isomorphism. So, we want to find a bijection, rather an inverse of f omega, and we claim that f omega inverse will serve the purpose. So, if we restate, f omega inverse of any point class gamma is omega star gamma star omega inverse by the definition of F omega inverse, and proceeding exactly the same way we get that F omega inverse is a group homomorphism. Now we see that F omega inverse and F omega, these two are inverse of each other. That is, if we take any element from pi 1 x x 0, let me take that element as class alpha and operate F omega composed F omega inverse on that, we ultimately get that it is equal to class alpha. Hence, pi 1 x x 0 and pi 1 x x 1 are isomorphic by the isomorphism F omega. Now, as a corollary to this theorem, we get that if x is path connected, then for any 2 points x 0 and x 1 of x, pi 1 x x 0 is isomorphic to pi 1 x x 1. Henceforth, in view of this result, we denote the fundamental group of a path connected space capital X by pi 1 x without mentioning the base point explicitly. Now, we define what we call simply connected space, that a topological space X is called simply connected if it is path connected and its fundamental group is trivial. So, in what follows, a trivial fundamental group will be denoted by 0. Let us suppose that we are given a continuous function between two pointed topological spaces. Now, what do we mean by continuous function between topological spaces, rather pointed topological spaces? It is actually a continuous function between the given topological spaces such that it carries the base point of the domain to the base point of the codomain. Now, we have constructed the fundamental groups corresponding to a pointed topological space x x 0, we call it pi 1 x x 0, and we have constructed the fundamental group pi 1 y y 0 corresponding to the pointed topological space y y 0. Now, the question is, can we construct a map between pi 1 x x 0 and pi 1 y y 0 if we are given a continuous function f between x x 0 and y y 0? The answer to this question is definitely yes, and not only that, this function is a homomorphism. Suppose f is a continuous function between the pointed topological spaces x x 0 and y y 0. We prove in this theorem that there exists a homomorphism f sharp from pi 1 x x 0 to pi 1 y y 0. By definition of continuous function between pointed topological spaces, we have that f is a continuous function from x to y, so that f x 0 is y 0. Now, we define f sharp from pi 1 x x 0 to pi 1 y f x 0 by f sharp alpha is equal to f composed alpha class. Now, if we just look at what is f composed alpha, then alpha is actually a loop based at x 0 and f is a function which takes x 0 to f x 0 or rather y 0. So, when we take the composition f composed alpha, it is actually a loop based at f x 0, and therefore, f composed alpha class is a particular element of pi 1 y f x 0. We claim that this f sharp is well defined. So, suppose I take class alpha equal to class beta then alpha is path homotopic to beta. Consequently, F composed alpha is path homotopic to F composed beta. That is, F sharp class alpha is equal to F composed alpha class, which is equal to F composed beta class, and that is equal to F sharp of class beta. Our next claim is that this F sharp is a homomorphism. Now, if I take any two elements from pi 1 x x 0, then suppose the elements are class alpha and class beta. In that case, alpha and beta are two loops based at x 0. So, we can form alpha star beta, which is again a loop based at x 0. So, F composed alpha star beta evaluated at any point t is equal to F of alpha star beta evaluated at t. Now, applying the definition of product of paths, we have in the first half of the interval, that is when t is between 0 and half, it is alpha 2t, and in the second half, that is from half to 1, it is beta of 2t minus 1, and therefore, the first part gives F composed alpha of 2t, and in the second part we get F composed beta of 2t minus 1. Thereby, we get F composed alpha star of F composed beta evaluated at the point t. Hence, F composed alpha star beta class is equal to class F composed alpha star F composed beta. So, if we apply the definition of F sharp, then F sharp of alpha composed beta is equal to F sharp of class alpha star beta, which is F composed alpha star beta class, which is F composed alpha star F composed beta class, and now we can split it up into two classes, that is F composed alpha class, composed F composed beta class. That means, F sharp alpha composed beta is F sharp alpha composed F sharp beta. That means, F sharp is a homomorphism. Now, the following are two very important properties of the induced homomorphism. If we take I from x to x, the identity map, then the induced homomorphism I sharp from pi 1 x x 0 to pi 1 x x 0 will be once again the identity homomorphism. Now, we look at the proof of this, that for each alpha taken from pi 1 x x 0, if we take induced homomorphism I sharp evaluated at class alpha, then that is equal to the class identity function composed alpha, and once again that is alpha. So, I sharp is a homomorphism. Now, the second one is that if we have a continuous function f from x 0 to y 0 and another continuous function g from y 0 to z 0, then we can compose them to get a continuous function g composed f from x 0 to z 0. We can take the induced homomorphism g composed f sharp, and without composing them we can form the induced homomorphisms f sharp and g sharp, and then after that we compose them, we get g sharp composed f sharp. we see that they are equal. How do we prove it? We take G composed F sharp operated on an element class alpha, that gives G composed F composed alpha class. Composition of maps is associative, so we can write G composed F composed alpha, the class of it, and that is equal to G sharp operated on F composed alpha class. Once again, F composed alpha class is F sharp operated on class alpha. So, ultimately we get G sharp composed F sharp operating on class alpha. So, we have that G composed F sharp is equal to G sharp composed F sharp. In view of this theorem, we can have a covariant functor pi 1 from the pointed topological spaces and continuous functions to the category of groups and group homomorphisms. This pi 1 is a covariant functor because it takes the objects xx0 of top star to the objects pi 1 xx0 in the category GRP, and whenever there is a continuous function f, we have a homomorphism f sharp between pi 1 xx0 and pi 1 yy0, satisfying the properties mentioned in the previous theorem. So, we have a functorial correspondence pi 1 between the pointed topological spaces to the category of groups. Therefore, the properties mentioned in the last theorem are referred to as functorial properties of pi 1. With this functorial correspondence, we end this module and wait till the following modules, where we take up several examples of topological spaces and find the fundamental groups of the spaces.